Okay, welcome once again to another flip session of chemistry. So in this session we're talking about the gas laws, right? So there's Boyle's law and there's Charles' law and there's a bunch of gas laws, ideal gas law. But today's gas law that we're going to take a look at is called Gay-Lussac's law. Okay, so a little bit about Gay-Lussac's law. It's named after the French chemist Joseph Louis Gay-Lussac. And it relates two variables, like most gas laws relate, two variables, when another third variable is constant. So Gay-Lussac's law relates how the pressure of a gas responds to a change in temperature. So how does the pressure change with a response to temperature at a fixed volume? Okay, so V is our constant in this case. So there's a direct relationship. As the temperature of a gas goes up, the pressure is also going to increase. So here's our expression for Gay-Lussac's law. Right? Our first pressure divided by our first temperature is going to be equivalent to our second pressure conditions over our second temperature conditions. You might be asking yourself, wait a minute, I've seen this before. This looks like someone else's law. It may remind you of Charles's law. Which is very similar, except volume is related to temperature under a constant pressure. Okay, so Gay-Lussac and Charles's law, very similar. Two different variables are being looked at here. Okay. So let's take a look. Let's look at what one of these problems looks like. So here's our problem. The initial temperature of a gas is at 293 Celsius and a pressure of 4 atm. So let's think about that for a second. Okay, we know we're going to use Gay-Lussac, and we know that the expression is P1 and T1, and there's going to be a second pressure and a second temperature. So it's a real good idea to write down some of these variables as we read through the problem. So the initial temperature, our T1, is 293 Celsius. But I know I can't leave it like that because we don't deal with the Celsius scale in gas laws, right? Because sometimes we could get 0 or negative Celsius, which is going to give us a negative value, which is sort of strange. So we're going to have to eventually convert this to Kelvin. And to do that, we're going to have to add 273.15, okay, to get that to Kelvin. So we're going to hold off on that. But just as a reminder here, we can't keep it in Celsius. And we have a pressure at this temperature of 4 atm, okay? So we know we're under 4 atmospheric pressures. The temperature is increased to 400 degrees Celsius. Okay, so once again, we're going to have to add 273.15 to get this temperature to Kelvin. We can't keep it in Celsius. What is the pressure in atm under this new temperature of 400 degrees Celsius? Okay, so let's think about this for a minute. We know there's a direct relationship between temperature and pressure. So if my temperature goes up, my pressure goes up. If my pressure goes up, those gas particles get closer and closer together. They rub past each other a little bit more, similar to the way if you were to enter a very congested subway cart, or a bus, or a room where there's a lot of people. If you're rubbing elbow to elbow, you're going to make some friction. And the room has a tendency to have a higher temperature, right? So if our temperature is going to increase from 293 Celsius to 400 Celsius, what should our pressure do? Should it go up? Should it go down? Should nothing happen? Okay, so let's think about that for a second. Okay, let's plug in these values here. So here's our solution. Okay. So our first pressure is at 4 atm. And our temperature I've converted to Kelvin. I've added 273.15. So our first temperature is 566.15 Kelvin. We do not know our second pressure. That's the question mark. And I also converted our second temperature, 400 degrees Celsius, to Kelvin by adding 273. Okay. So if we transpose some of these variables in Gay-Lussac's law, we get P2, which we don't know, is going to be T2 times P1 divided by T1. So we're simply going to plug in these values here. Okay. And here's what we get for an answer. Okay. So if we look at this, here's our T2, and here's our P1, and our T2. Okay. If you notice here, the kelvins are going to cancel. A Kelvin for a Kelvin. So we're left with the unit that we desire, which is the atm. And our final pressure is going to be 4.76. Now, does it make sense? Should our pressure go up? Well, our temperature went up from 566 to 673. So our pressure should do the same, right? So our pressure increases because there's a direct relationship between temperature and pressure. All right. So this is one example of Gay-Lussac's law. There's going to be a second video here, as usual, where you practice one of these laws using Gay-Lussac's equation. All right. Good luck with these, and I'll see you next time.